In this video, we will discuss about the thermal stresses in the compound bar. Okay, so compound bar. What do you mean by compound bar? It is a combination of two or more bars. Here we have the bar 1 is there and bar 2 is there. Okay, so this is a compound bar. And if it is subjected to thermal stresses, it means if it is subjected to change in temperature, what are the stresses developed in the compound bar, that we need to derive here. Okay, so first consider bar 1 and bar 2 forms compound bar. As shown in figure. See here, this is bar 1, this is bar 2, and it's forms a compound bar. And the length of the compound bar, is L. L equal to length of the compound bar. Okay, and this compound bar is subjected to the increase in temperature. The bar is subjected to increase in temperature. That will be equal to delta T. Okay, and here we have so many notations here. So for bar 1, just I'll write one by one. Alpha 1 and alpha 2. What is alpha 1 and alpha 2? Here the alpha is related to first bar. This is first bar, and alpha 2 is related to second bar. Is the coefficient of thermal expansion. Thermal expansion of bar 1 and 2. Okay, so next, delta T is same for both the bars, and L is the length of the bar, and E, what is the E here? E1 and E2. E1 and E2 are equal to Young's modulus. Of bar 1 and 2 here. Okay, and what are the sigma and sigma 1 and sigma 2 here? If you see this in the diagram, this is sigma related to 1 and this is sigma related to 2. These are, sigma 1 is related to the compressive stress. It is compressive stress, and sigma 2, what is sigma 2 here? It is related to the tensile stress. Tensile stress in bar 1 and 2 here. So these are all the notations here. Okay, and DL equal to the deformation induced when compound bar is subjected to increase in temperature. That is deformation due to increase in temperature delta T. I will explain the diagram once again. The total L is the length of the compound bar 1 and 2. This is the L. Okay, next we have alpha T L of 1. This is the first bar. This one is the free expansion of the bar 1. That will be equal to alpha into delta T into L of the 1. Okay, so now next the bar 2, come to the bar 2, when it is the free expansion of this bar is alpha into delta T into L of 2 here. It will undergo this much of expansion. First one will undergo this much of expansion. It is more, this is less here. Okay, this is the free expansion due to change in temperature. Okay, next the dl, this is the deformation due to increase in temperature. Deformation here it will be there of both compound bar. Okay. Now next, if you come to the sigma L E of 1, that is, if you see this one, here is the line, it is the deformation of the bar. So obviously when it is deformed freely here the compressive stresses will be developed. That compressive stresses are the sigma L by E of first one. Okay, up to this line it will be compressed. So here what happened, this is the free expansion, and next you have to apply the longitudinal, that is the tensile stress, tensile the deformation, that is the elongation from here to here, because you need to balance to this line, that is sigma L divided by E of the second bar here. Okay, we will go one by one here. So this is how the diagram explains. So one more we need to assume, that is assume alpha 1 is greater than alpha 2, that is coefficient of free expansion of first one is greater than the coefficient of free expansion of the second. Per unit change in temperature, the expansion is this is more compared to this here. So also we need to consider second one, it undergoes the compound bar undergoes increase in temperature. Okay, increase in temperature. We have two cases. One is decrease in temperature. If decrease in temperature, obviously there is a compression. But now here we are deriving the equation by considering increase in temperature, delta T. Okay, that is the second assumption here. Now, first I'll take the free expansion of bar 1, that is free expansion of bar 1. Okay, that will be equal to how much free expansion? It will undergo this much due to temperature, alpha into change in temperature into L, that of first one. You can also write this one as, that is alpha 1, because alpha is differ from material. Alpha 1 change in temperature is same for both, and this is L here, that is L. Okay, this is L1, how much it will undergoes. So second one, next, that is the free expansion of bar 2 is how much? That will be equal to, here it will undergo only this much here. What is the value here? Alpha into delta T into L of 2. Better we'll write first and second like this. Alpha into delta T into L of is the 1. This is the free expansion of bar 1 and bar 2. These are finished now. Now, because of this free deformation, the DL, that is deformation due to increase in temperature, is the line is here, from here to here. Okay. So obviously there is a compressive deformation in the bar 1. Okay, compressive deformation in the bar 1. Compressive deformation in bar 1. How much is compressive deformation? This much, because it will compress. The deformation is this much. That is sigma L divided by E of first one. Okay. So what will be the final deformation of the bar 1 here? Final deformation, it means the alpha into delta T of L1 minus this much. This is the final deformation of the bar 1, right? Bar 1. So final deformation of bar 1, that will be equal to, I'll write dl of 1. Final deformation of bar 1 equal to total this, that is alpha into delta T into L of 1 minus, right, minus this much, that is sigma into L of E of first one. This is final deformation. Call this one as 1, equation 1. Now we should also write the final deformation of the bar 2, right? Bar 2. Here we wrote already the free expansion, alpha into delta t into L of 2 here. Okay. Next, the elongation, that is elongation of bar 2, right? Because it will undergo elongation, not compression. Here this will be compressive, first one. That will be equal to how much? Here sigma into L divided by E of 2, right? This is the elongation deformation. Now how much is the total final deformation of the bar here? This plus this, right? Therefore final deformation of bar 2 equal to final deformation of bar 2 equal to how much I can write here? This plus this, right? Alpha into delta t into L of 2 plus sigma L of by E of 2. Call this one as equation number 2. Now this is bar 1, this is bar 2. Now you need to equate the final deformation here, right? So equate 1 and 2. Equate 1 and 2. Where is the first one here? Alpha into delta t into L of first one minus sigma into L divided by E of first one equal to, come to the second one, alpha into delta t of L of 2 plus sigma L divided by E of 2. Okay. I just interchange the signs here. This will be minus, I'll make minus alpha into delta t into L of 1 plus sigma into L divided by E of 1 equal to minus alpha into delta t into L of 2 minus sigma into L of divided by E of second one. Okay. Now I take the interchange, the sigma into L divided by E of first one. If I take this one in the left side plus sigma into L divided by E of second one equal to, if I take this one in the left side here, alpha into delta t L of 1 minus alpha into delta t of L of 2. L of 2 here. Okay. So I can take delta t as the common here, right? So this I can write it as alpha into L of 1 minus alpha into L of 2. If I take common, this is delta t, and this is sigma into L divided by E of first plus sigma of L divided by E of second. Okay, this is the derivation when the bar is subjected to the compound bar, for the compound bar. Okay, the different cases, if L1 equal to L2, the one case is there, we need to consider that one, because for in this case the L1 equal to L2 equal to L, both compound bars having the equal length. So if L1 equal to L2, how about the equation here? That is sigma by E sigma 1 by E1, because all L cancels, this L, L1, L2 and this L cancels. I'll write the final equation, sigma 1 by E1 plus sigma 2 by E2 equal to alpha 1 minus alpha 2 into delta T. Okay, this is the derivation we need to derive here.